Hello. In this session, we're going to talk about representations of floating point numbers. Thus far, we've talked about integer representations, but floating point representations are considerably different. Fractions, decimals, are difficult to represent in computing systems because they have to represent both very, very large numbers and very small numbers in the same format. For example, this particular number, negative 357.02186, can be written as a power of 10 that's 10 to the 5th by sliding the decimal place to the left, or as 10 to the negative 4th by sliding the decimal place to the right. What we have to do is pick one representation that works for all numbers. And so that involves a sign bit, an exponent, and a mantissa. Now, the exponents can be either positive or negative. So in order for us to accommodate that in a fixed width field, we have to divide the fixed width field in roughly a half. So if we have 99 possible digits, 50 is roughly in half, and so we subtract 50 from the exponent that we want to get the actual exponent. This is called an excess notation, and the example above uses an excess 50 notation. So let's take that earlier number and normalize it into a sign, exponent, and mantissa. So the first step is to shift the decimal place so that there's a leading 0. So we just move it over to the left. And then we also have to increase the power so that it's 10 to the 3rd. Then we're going to truncate off the bits that we can't represent. So in this particular example, this base 10 number, we're only going to hold 5 digits. Then what we have to do is encode it using the excess 50 exponent notation. In order to get excess 50, to get a real exponent of 3, we add 50 to that to get 53. The number is negative, so we have a leading 1. So the final encoding is 1, indicating negative, 53, indicating the exponent of 10 to the 3rd power, and then the digits of the mantissa, 35702. Now, numbers in computing systems are base 2 numbers, not base 10 numbers. And so the IEEE has come up with a standard for representing single precision floating point numbers. It consists of 1 sign bit, 8 excess 128 exponent bits, and 23 mantissa bits. And it's important to understand that the mantissa is not encoded as an integer. The mantissa is encoded as a fraction. So these are not positive powers of 2, but negative powers of 2. So they include a half, a quarter, an eighth, a 16th, and so on. So let's encode this example using the IEEE 754 encoding. The first thing to do is to understand that the sign is a 1. It's negative. So we take that sign bit off and then we represent the positive number, so 357.02186. The next step is to convert that to a power of 2. So I find the largest power of 2 that when I divide it, I get a leading 1 for that number. That power of 2 is 2 to the 8th, or 256. So when I take 357.02186 and I divide it by 256, I get 1.3946, and so on. Now we take a note of the exponent. This is a factor of 2 to the 8th. So we're going to have to encode that in excess 128 notation. So to do that, we add 127 to it to get 135, and then we make a simple binary representation of 135. So those bits right there represent what the exponent will be in our notation. So we're going to have a leading 1 and then these bits. What's left is to convert the mantissa. So we drop the leading 1 and we want to represent this fractional part. The reason we drop the leading 1 is because there will always be a leading 1 and there's no reason to encode it. So we have to encode 0.3946166,406. So we rewrite this as the sum of fractional powers of 2. It turns out that if I add 1/4 plus 1/8 plus 1/64 plus 1/256 and so on, I get a pretty close approximation of that decimal number. So then I take those numbers, a 4th, an 8th, a 64th, and so on, and I encode those as binary. And so these are the bits. Remember, these are fractional bits, so the leading 0 represents 0 times 1/2, or 0 times a half. plus 1 times a quarter, plus 1 times an eighth, and so on. And now I have all the bits that are necessary. I have the leading 1, I have the XS128 exponent, and I have the mantissa bits. And all I have to do is arrange them. And this is the IEEE 754 representation. So the question is, why do we go to all this effort for floating point in our CPU? And the answer is, it simplifies the CPU hardware. There are two cases then for adding or subtracting floating point binary. When the exponents are the same on two floating point representations, then I can just add or subtract the mantissa and it works as expected. If the exponents differ, then I can shift the mantissa to the left or to the right by the difference between the exponents and then perform the addition as expected. And so this overall simplifies the CPU hardware for addition and subtraction. So the main point of all this is that the IEEE formats in 2's complement are all about making the CPU as fast and inexpensive as possible. So, in summary, converting decimal floating point to binary floating point is not easy. The representations that we use are a sign, an XSN exponent, whatever n is, and then a fractional binary mantissa. And the end goal of these representations is to make the CPU fast and inexpensive.